In mathematics, a differential operator is an operator defined as a function of the differentiation operator. It is helpful, as a matter of notation first, to consider differentiation as an abstract operation that accepts a function and returns another function. This article considers mainly linear operators, which are the most common type. However, nonlinear differential operators, such as the Schwarzian derivative, also exist. Definition: assume that there is a map from a function space to another function space and a function so that is the image of i.e. a differential operator is represented as a linear combination finitely generated by and its derivatives containing higher degree, such as where the set of non-negative integers is called a multi-index, called length, of functions on some open domain in n-dimensional space, and the derivative above is 1 as functions or, sometimes, distributions or hyperfunctions, and or sometimes, notations. The most common differential operator is the action of taking the derivative itself. Common notations for taking the first derivative with respect to a variable x include, and when taking higher nth-ordered derivatives, the operator may also be written, or the derivative of a function f of an argument x is sometimes given as either of the following. The D notations used in creation is credited to Oliver Heaviside, who considered differential operators of the form in his study of differential equations. One of the most frequently seen differential operators is the Laplacian operator, defined by another differential operator is the theta operator, or theta operator. Defined by this is sometimes also called the homogeneity operator, because its eigenfunctions are the monomials in Z. In n variables, the homogeneity operator is given by as in one variable, the eigenspaces are theta are the spaces of homogeneous polynomials. In writing, following common mathematical convention, the argument of a differential operator is usually placed on the right side of the operator itself. Sometimes an alternative notation is used, the result of applying the operator to the function on the left side of the operator and on the right side of the operator, and the difference obtained when applying the differential operator to the functions on both sides, are denoted by arrows as follows. Such a bidirectional arrow notation is frequently used for describing the probability current of quantum mechanics. Del. The differential operator del, also called Nabla operator, is an important vector differential operator. It appears frequently in physics in places like the differential form of Maxwell's equations. In three-dimensional Cartesian coordinates, del is defined. Del is used to calculate the gradient, curl, divergence, and Laplacian of various objects. Adjoint of an operator. Given a linear differential operator T, the adjoint of this operator is defined as the operator such that where the notation is used for the scalar product or inner product. This definition therefore depends on the definition of the scalar product. Formal adjoint in one variable in the functional space of square integrable functions. The scalar product is defined by where the line over G denotes the complex conjugate of G. If one moreover adds the condition that f or G vanishes for n, one can also define the adjoint of T by this formula does not explicitly depend on the definition of the scalar product. It is therefore sometimes chosen as a definition of the adjoint operator. When is defined according to this formula, it is called the formal adjoint of T. A self-adjoint operator is an operator equal to its own adjoint. Several variables if omega is a domain in Rn, and P a differential operator on omega, then the adjoint of P is defined in L2 by duality in the analogous manner, for all smooth L2 functions f. Since smooth functions are dense in L2, this defines the adjoint on a dense subset of L2. P** is a densely defined operator. Example: the Sturm-Liouville operator is a well-known example of a formal self-adjoint operator. This second-order linear differential operator L can be written in the form. This property can be proven using the formal adjoint definition above. This operator is central to Sturm-Liouville theory, where the eigenfunctions of this operator are considered. Properties of differential operators. Differentiation is linear, i.e., where f and g are functions, and a is a constant. Any polynomial in D with function coefficients is also a differential operator. We may also compose differential operators by the rule some care is then required. Firstly, any function coefficients in the operator D2 must be differentiable as many times as the application of D1 requires. To get a ring of such operators, we must assume derivatives of all orders of the coefficients used. Secondly, this ring will not be commutative. An operator GD isn't the same in general as DG. In fact, we have, for example, the relation basic in quantum mechanics. The subring of operators that are polynomials in D with constant coefficients is, by contrast, commutative. It can be characterized another way. It consists of the translation invariant operators. The differential operators also obey the shift theorem. Several variables. The same constructions can be carried out with partial derivatives. Differentiation with respect to different variables giving rise to operators that commute. Ring of polynomial differential operators. Ring of univariate polynomial differential operators. If R is a ring, let B the non-commutative polynomial ring over R in the variable D and X, and I the two-sided ideal generated by dx x d1, then the ring of univariate polynomial differential operators over R is the quotient ring. This is a non-commutative simple ring. Every elements can be written in a unique way as a R-linear combination of monomials of the form. It supports an analog of the Euclidean division of polynomials. Differential modules over can be identified with modules over. Ring of multivariate polynomial differential operators. If R is a ring, let B the non-commutative polynomial ring over R in the variables, and I the two-sided ideal generated by the elements for all where is Kronecker delta. Then the ring of multivariate polynomial differential operators over R is the quotient ring. This is a non-commutative simple ring. Every elements can be written in a unique way as a R-linear combination of monomials of the form. Coordinate-independent description. In differential geometry and algebraic geometry, it is often convenient to have a coordinate-independent description of differential operators between two vector bundles. Let E and F be two vector bundles over a differentiable manifold M. An R-linear mapping of sections P. Gamma is said to be a kth-order linear differential operator if it factors through the jet bundle JK. In other words, there exists a linear mapping of vector bundles such that where JK, gamma is the prolongation that associates to any section of E its k-jet. This just means that for a given section S of E, the value of P at a point xm is fully determined by the kth-order infinitesimal behavior of S in X. In particular, this implies that P is determined by the germ of S in X, which is expressed by saying that differential operators are local. A foundational result is the Petre theorem, showing that the converse is also true. Any local operator is differential. Relation to commutative algebra. An equivalent, but purely algebraic description of linear differential operators is as follows. An R-linear map P is a kth-order linear differential operator. If for any k plus 1 smooth functions we have here, the bracket is defined as the commutator. This characterization of linear differential operators shows that they are particular mappings between modules over a commutative algebra, allowing the concept to be seen as a part of commutative algebra. Examples. In applications to the physical sciences, operators such as the Laplace operator play a major role in setting up and solving partial differential equations. In differential topology, the exterior derivative and Lie derivative operators have intrinsic meaning. In abstract algebra, the concept of a derivation allows for generalizations of differential operators which do not require the use of calculus. Frequently such generalizations are employed in algebraic geometry and commutative algebra. See also Det. In the development of holomorphic functions of a complex variable z equals x plus iy, sometimes a complex function is considered to be a function of two real variables x and y. Use is made of the Wirtinger derivatives, which are partial differential operators. This approach is also used to study functions of several complex variables and functions of a motor variable. History. The conceptual step of writing a differential operator as something freestanding is attributed to Louis-François Antoine Arbogast in 1800.